we are doing the centrifuge testing. Of course, first point I would like to clarify is there is, although we call the ones we looked at yesterday as a static test, centrifuge is always spinning, right? So there is nothing static about those tests either. But what we mean by dynamic centrifuge modeling is that you got on top of the rotation, you need to be able to shake the model while it's still going around. And that's why it is complicated. I don't know if you have seen shake tables in structures lab before. Those are quite complicated, big tables. The largest shake tables are like 5 meters by 5 meters, and to shake them is quite complicated. What we are attempting is to do that while it is going around on a centrifuge. So it is doubly or triply more complicated. But I'll explain how it is done. Firstly, I'd like to say that it's possible to apply dynamic loads. Until now, I've built 2, 3 earthquake actuators. So I've been doing this for a long time. But earthquakes is only one type of dynamic loads. It's interesting because earthquakes do create a lot of damage, but you can also model other things like blast loading, wind loading, and other types of dynamic loading. As an example, one of my PhD students recently was trying to look at HS2, the fast moving train, and we could model that in the centrifuge again. So there are other dynamic loads as well. FE modeling of these problems is possible, but it is quite complex, and you normally require some specialist codes. Only recently, commercial codes like FLAC, FLAC 2D, FLAC 3D, FLACSys 2D, 3D became available. But until then, almost every research group had their own specialist dynamic code. ICFEEP, for example, the Imperial College one. We use Swandyne, which is developed by Swansea, and so on. There are some advantages and disadvantages of using commercial software like FLACSys, but we'll come to that tomorrow and day after when you get a chance to play with the FLACSys software. Okay? But most important thing is really the constitutive model that are available. When you're doing dynamic problems, the constitutive model that is there should be able to handle this type of cyclic behavior of the material. Especially for soils, we talked about yesterday that the soil is non-linear and also plastic. It also has this other unfortunate habit of trying to change volume as well. So you can't look at soil behavior just in stress space. So you can, although we traditionally draw more circles are totally in a stress space, right? But what is important is what is happening on the third axis, where the void ratio or volume, specific volume, is also changing. So your constitutive model needs to be able to handle that as well. On top of that, you need these non-reflecting boundaries at the end of the mesh, because the real soil is a semi-infinite extent, but you can't make the mesh go occupy the whole world, right? You have to have boundaries. Where you have boundaries, you must make sure none of the stress waves are getting reflected back. That's in fact a problem in centrifuge testing as well, and I'll show you later on in this lecture how we handle that. Typically, I mean, this is a good problem to look at, liquefaction of ground. We talked about this yesterday already, so I'm not going to go into the details. Basically, what we are saying is the soil will lose its effective stress almost to zero as the excess pore pressures build up. And the excess pore pressures build up because you're trying to shake the soil. It wants to change its volume, but there's no time for the water within the soil to escape. You can actually do this in the QP- plane. I don't know if you use this framework. I have a pen here somewhere. Right? Oh, they've taken the pens again. Somebody has the markup in here? शॉप की साइड पे वही चला गया. But what we can model in the centrifuge is not, yes, the soil behavior and sand boils and all those things. I even showed you examples of where we could see this in the experiments yesterday. But really, what we are interested in is if there's a building that is constructed on soil like this, we can predict how much it will settle and rotate. Thank you. So you can plot, if that's my Q and this is P dashed. P dashed is the main confining stress, Q is the deviatoric stress, and the critical state line goes like that. By convention, we draw two lines. So initially, when the soil is just horizontal and before the earthquake, you don't have any Q and you probably have some P dashed. Okay, P dashed is basically sigma 1, sigma 2, sigma 3. These are the principal stresses, so it's basically mean confining stress, and Q is sigma 1 minus sigma 3. You can also put dash, it doesn't make any difference. So initially, my stress rate will be somewhere here. As I try to shear the soil, what it'll do is, so the pore pressure is going up, U is going up, because P dashed is P total minus U. If U goes up, this comes down. That's why I'm traveling this way. Okay? All is great until I come to here, almost near zero, P dashed and Q. Because I'm hitting the critical state line here, I tend to dilate from here and go up to its critical state up the line, corresponding to its void ratio. And this means that what was coming here has to go in the other direction, and it can only do that if my U is now starts to decrease. In other words, it has to create suction. So this is the soil behavior we expect. There's a framework, and you want to see whether the framework works for the real soil or not. So, of course, at many locations, these are the pictures we have taken. This was my former student and current colleague, Professor Haig. At one of the things that happened in Bhuj earthquake was that because it's all salt marshes, run of Kutch, when the sand liquefied, the salt water came to the surface and dried out and left the salt. So we could exactly map how big the sand boils were even 10 days, 20 days after the earthquake. But that sand boils, well, they're interesting. Nobody is actually worried that there's no structure, right? It's all fine. It regained its strength. Nobody worries. But the real problem is things like these are from the Chichi earthquake, 921 Chichi earthquake, where they had a lot of these containers which hold liquid, and this all the soil here liquefied. This is the Taichung harbor, and you can see these cylindrical bulk fluid holding tanks lost their roofs. Why? And this is a very interesting structures problem, because I got a cylinder and with fluid, when I shake it, the cylinder wants to go oval and come back, right? But I got a shell sitting on the top, and the only way I can accommodate this is if my shell pops out. And so people look at this fluid structure interaction as well. Again, I've shown you this many times. We don't need to spend time. But these kind of problems. And that was 1964, the year Professor Agnihotri and I were born. But it keeps going even now, right? This is from Adapazari earthquake, the Turkey earthquake of 1999, and even more recent ones I can show you, where buildings collapse like that. And sometimes in civil engineering, although you have done everything right and constructed your building perfectly, if your neighbor has cut costs, then you will be in trouble because this whole building fell on the other one. So choose your neighbors carefully. Don't settle next to cheaper neighbors. So clearly, these are quite complex problems where we're talking about interaction between the soil and the structure, and also how the soil behavior changes under cyclic loading. Now, dynamic centrifuge modeling offers a realistic chance of recreating these failures at laboratory scale. Now, one of the big advantages of doing centrifuge testing is that we can actually put instruments and see what is happening before the earthquake, during the earthquake, and also after the earthquake, which means we can track the movement of the structure towards failure. And then you can also use this data to validate numerical models. So you got quite a lot of advantages. Before we kind of jump in, I want to cover how actually what is the bit of earthquakes that we want to model. So typically, you can have a problem where you got a building, say, supported on raft and piles. And this is, say, a uniform bed of sand, and I got bedrock at the bottom. When the earthquake happens, you'll have a slip, or there are many faults in the earth system, and the fault somewhere deep below will undergo a sudden slide. That's what generates the earthquake. So that slip and the following elastic oscillations are what we see as vibrations. So those travel very quickly through the bedrock. Because bedrock is quite solid, they go very quickly. And every point along the base will see these vibrations. So every point will then start to shake the soil in that direction, and you get the propagation upwards. These are called horizontally polarized shear waves, or SH waves. And these SH waves are the ones which do most damage. You will get a component of P waves as well, but P waves don't have that much energy in them. SH and SV waves are the big ones, but SH is the one because that is the horizontal component we are interested in. Okay, so that is the basic oscillation. Let's do some maths. Suppose I take an element of soil, say somewhere here. I'm going to consider one element of soil there. And I'm going to look at what stresses will it have. So horizontally, let's say I have sigma x, vertically I have sigma y, and I'll also have tau xy on the vertical planes. Yeah. So this is a standard, this is what you would use to draw mosaic, for example. Now, if I consider equilibrium of that soil element, then I can write in the horizontal direction the change of sigma x in the x direction. So delta or dou, partial derivative, delta sigma x over dx. In the other direction, dou t tau xy over dou y, plus any force I have in the x direction. Must be, if I add all of them, it should be 0. Then I know my element is in equilibrium horizontally. Similarly, in the vertical direction, dou tau xy by dou x plus dou sigma y by dou y plus y equal to 0. So this big X and big Y are the body forces in X and Y direction. Normally we don't have, we'll have Y, but we don't have any x. Only during earthquake you will get x because of the inertial forces. Now, let's keep this quite simple and say I'm going to, a real earthquake will normally be something like maybe some multi-frequency oscillation like that. Let's get rid of all that complication and say you guys can still see this? Oh, great. Let's say I'm only going to consider a nice sine wave like this. So that is my the input motion. So this kind of motion can be characterized by amplitude A and the frequency is omega. So then I can write my displacement will be A sine omega t. It's just a harmonic motion, right? And I put minus just to make my maths easy. In other words, what we are saying is I'm not going to do that. I'll start the other way. It doesn't really matter. It's still a sine wave. So if I write my displacement like that, my velocity will be dx by dt. So a omega cos omega t, acceleration differentiate again, a omega squared sine omega t. So far, straightforward, right? So my body forces, in the y direction, I got gravity, g times say rho is the density. So that density times g should give me my vertical body force. Minus just means that it's acting from top to bottom because g is that way. X on the other hand will be this acceleration times rho. Rho is the density. So my x is rho a omega squared sine omega t. So I can plug these back and those should be the x and y forces. Now when I want to do centrifuge testing, we want at the model scale, yesterday we said that the acceleration should be increased by n, right? Because you scale the model down by factor of n and therefore the acceleration should be increased by ng, right? Now, I can't say when it comes to centrifugal acceleration, I'll use n, but when it comes to shaking acceleration, I'm not going to do that. That's not right because the acceleration is acceleration, you have to be consistent. So, for the model scale, I need to increase my acceleration by a factor of n. So, n omega squared, n a omega squared, and this sine n omega t. So, this acceleration magnitude is now n times bigger compared to what we had in the prototype scale, as it should be. Then I can get my velocity by integrating that and displacement by integrating velocity. And now I can see my amplitude has come down by factor of n, which is also consistent with our scaling laws. The displacement should all be reduced by factor of n, right? So it is consistent. But to do this, we fiddle something. Can you spot what did I change? If I go back to the previous slide, frequency was omega t. Here, frequency is n omega t. And this is a bit unfortunate. This is not working in our favor. I can match the acceleration and I can match the displacement perfectly, but I can only do this if I shake my model n times faster than the actual earthquake frequency. This is a very simple way to demonstrate why frequency in the centrifuge test has to be n times bigger, just to make the whole set consistent. So once you do that, we can write a set of scaling laws for the dynamic scaling laws. Until here, we have done yesterday. All these are exactly same as yesterday. Now the displacement, velocity and acceleration. Acceleration is n times, this is also consistent. Frequency is now n times larger, and reciprocal of frequency is time period, so that will be 1 over n. Agreed? Right. So, yeah.
Normally, like earthquake motions will be there, and sinusoidal waves will be doing in the lab. Like, can I make it in any other method, like equivalent to earthquake motion, like that?
Yeah, I need to increase my amplitude of the shaking by factor of n, because acceleration should be n times larger, and the time scale should be n times smaller. If I do that, then it will match.
No, not that. Like earthquake motions, like they are not regular.
Oh, yeah. Oh, you mean this? I'll come to that. Okay. We will scale them also the same way. I'll show you in a second. So if you want to model the earthquake problems effectively, we need to subject the centrifuge model in flight while it is spinning to lateral shaking to simulate earthquakes. But then compared to real earthquakes, which have a frequency range typically between 1 to 5 hertz and a duration of 20 to 90 seconds, minute and a half is about most earthquakes. So the scaling laws now mean that, say if I want to do this test at 100 G, I need to shake my model at 100 to 500 hertz. Okay? And the duration, if I wanted to model 20 seconds to 90 seconds, then that will reduce to 200 milliseconds to 900 milliseconds. Pretty fast. Yes. And this is why it is complicated. It also means that once you are applying the earthquake so fast, my instrumentation needs to respond at this high frequency. My data acquisition needs to log, typically we log at about 6 to 10 kilohertz per channel. So everything gets complicated. And this is why it's not so straightforward to do centrifuge testing for earthquake problems. But it has been done. As I said yesterday, there are about 85 centrifuge centers around the world. About 20 to 30 can all do earthquake work as well. Right.
Sir, but for me, core water pattern is there.
Yes.
But that much of microscope, how it will be?
It will. I'll show you. It will produce the pore pressure, because pore pressure is same as stress, right? So it will produce, and the scaling law is 1. So the pore pressure you will get in the centrifuge model will be same as in the field. Exactly the same.
But like permeability, we will be very good. You said like we have to create a particle.
Yes, we will come to permeability separately. Okay. So first difficulty is that we need to shake it fast and log the things quickly. You had a question about the type of input motion earlier, right? Let me answer that first. Now, there are 2 schools of thinking about this. One is we have recordings of past earthquakes. If you go to the PEER, Pacific Earthquake Engineering database, there are past earthquakes, lots of them, records are available. So we can pick the one we want and model, use that to create the earthquakes in the centrifuge. There is another alternative is to use the simple sinusoidal motions. And my professor Andrew Schofield always said we learn more from sinusoidal motion. The reason is when you are applying sinusoidal input motion, it is very clean input. There is one frequency and an amplitude. So you can then see what the soil and the structure are doing in response to that shake. If you put, say, something like the El Centro earthquake or Kobe motion, then that has quite a lot of different frequency components and the amplitude is constantly changing. I'll show some traces to you. Then can we still interpret what's going on to our soil? Well, his argument is you can't, because everything is changing, so it'll be like garbage in and garbage out. Whereas if you put sinusoidal motion, it is all quite clean and you can track if if the natural frequency of the soil is changing, we can track it. So both are true, and many people, even with sophisticated shaking tables, still use sinusoidal motions where you want to study the fundamental behavior. But say you got a structure in San Francisco and you want to make sure that that particular structure with the soil underneath it is not going to get into resonances for maybe 5, 6, 7 types of earthquake motions, you can apply different input motions and show it will all work okay. So both approaches are followed. Depends on what is it that you're trying to do. But one thing I'd like to say is, although we have input motions recorded in the peer database, nobody in the world can tell me at any given site in the world what the next earthquake's frequency content is going to be. At best, seismologists can say, in this area, you can expect magnitude 6 or 6.5 earthquakes. And then you say, two things you should not ask a seismologist: when will the next earthquake happen? They have no idea. Nobody can predict that. The other thing, even worse, is to go and ask them, what frequency content will it have? And they'll say, go home. Okay, so there's no cat and else chance of telling you what the frequency content is. So basically, the future earthquakes are always going to have some unknown frequency content. Amplitude, maybe we can guess, but not the frequency content. So is it not better, because we don't know the frequency anyhow, to use the sinusoidal motions? That seems to be a reasonable argument, And also, since this whole course is about failure mechanisms and how do we understand failure mechanisms and use them for design, for our purposes, if you do the sinusoidal motions, it's so much easier to identify the failure mechanisms. Okay, and I'll show you some example in the lecture after tea. This is the other point you are asking. Magnitude of excess pore pressures generated in the soil during the earthquake should depend on, the amplitude of the pore pressure or the magnitude of the pore pressure should be the same as you would get in the field, because it has scaling law of 1. Pressure has scaling law of 1. However, if the rate of loading changes, will the pore pressure, rate at which pore pressure generates changes? Magnitude will be the same, but because we are applying our earthquake faster, will it generate quicker? And we can do this kind of thing, like even in structural dynamics, people actually say that the rate dependent effects are not that big. In soils, especially under earthquake engineering, we assume that the rate dependent effects are not too dominating. But you can prove this kind of thing using FE, for example. But there is one problem we ran into, which is, yesterday, is this power not going to come? At some point, my computer will run out of battery. Anyhow, yesterday we said that for consolidation and all the diffusion based events, our scaling law for time is 1 over. So for consolidation, the time is 1 over n squared. Remember, I was saying it is like time machine, and we can model something that will happen in 10 years by running the centrifuge for 9 hours. But we just said that for dynamic events, the time is 1 over n. So this is a problem, clearly a fairly big problem. So if I want to model the soil with water in it, saturated soil, then my consolidation will be scaling as 1 over n squared, but my dynamic time or the rate at which the pore pressure builds up will scale as 1 over n. And this is a nightmare because I'll generate the thing too quick and the dissipation will happen too slow. So we need to somehow fix this. What do? We have two options. One is we can change the pore fluid. So instead of using water as the pore fluid, I can use viscous liquids as pore fluids. When I started my PhD, we used to use silicone oil. And silicone oil works well, but it's very expensive. It's actually used in medical applications. More recently, we started using this methyl cellulose. Methyl cellulose is very cheap. It's basically like it's cellulose, so it's like rice powder. So you can mix with water and make the soups thicker. For example, when you have soup, it has a lot of methyl cellulose, so that the soup feels thicker. Okay, so it's edible, so it's non-toxic, and we use that, and we can adjust the viscosity of the fluid by adding more or less powder, and we can get anywhere between 50 to 100 easy. So we will use fluid that is 50 times more viscous, 50 centistokes or 100 centistokes, by mixing it with this methyl cellulose powder. But then you need to prove that if you substituted your pore fluid, then you're not changing the actual constitutive behavior of your soil, because you now said, no, I'm not going to use water, which is the natural fluid. I'm going to use this methyl cellulose, right? So there were people like a fourth-year student called Eaton long time back, and more recently Zheng et al. They basically did cyclic triaxial tests by saturating the sand samples with water and also methyl cellulose at different viscosities. And what they have shown is that the stress strain behavior remains unaltered even if you use viscous fluid in it. Okay, so this is the verification. So by now changing the pore fluid, what we have done is the permeability you were mentioning earlier is now reduced by a factor of n, because permeability of soil depends on not just the gaps in between the soil grains, it also depends on the pore fluid. So because we changed the pore fluid, the permeability effectively reduced by a factor of n, which means when the pore pressure is building up, say I applied a sinusoidal motion like this, and I'm looking at the pore pressure, it will start and it will do that. And after the earthquake is finished, it will start to dissipate. So the rate at which it dissipates in the post-seismic period and the rate at which it builds up in the co-seismic period will match by doing this pore fluid substitution. Otherwise, the rate of buildup will be too quick and dissipation will be too slow. So we shouldn't be doing that. So a lot of thought has gone in to creating all the bits you need to do this dynamic centrifuge test. It's not just building an actuator, putting soil in it and shaking it. You need to know the theory, and you will get problems and you need to solve the problems. Okay. What other equipment do we need? So for doing dynamic centrifuge tests, we probably need, obviously, shakers. The earthquake actuator or shaker, which is capable of shaking the model in flight. Now, typically, let's say my model container is about a ton with the soil in it. So if I'm at 50 G, the force will be 50 tons and in the radial direction. And if I want to apply something like 0.25 G earthquake on it, I need to hit that with 25 tons in the lateral direction to model 0.25 G, which means that my shaker needs to be able to produce big force. Yeah. And also it has to do it quickly, which means the power requirement is quite high. That's the first point. The second point is the boundary problem. Just like in finite element analysis, where you encounter boundaries, you have to do something special. In the centrifuge also, the model containers are always going to be limited. So the boundaries need to be carefully thought about. And I'll talk about that. And instrumentation obviously should respond quickly. Typically, we use accelerometers. We can measure stress and strain, either using PIV or pressure cells and so on. So instrumentation is more or less the same as anything else. As I said, we've done quite a few of these shakers myself. As I said, the biggest thing is that you need huge quantity of energy being delivered in very quick time. That means the power has to be very big. Typically, what are available at the moment, I put here, mechanical actuators. I built a couple of those. Servo-hydraulic shaker, that's the one we are using in Cambridge and elsewhere in the world as well. And this is the one we are trying to build for IIT Bombay at the moment. You can also have electromagnetic shakers. Only Japanese have one or two of those. So the first one I built is the stored angular momentum actuator, what we call SAM actuator, and it is very simple. The whole device we built in Cambridge costed us about less than 20,000 pounds, if you don't count my salary. So it's very easy. All it has is a cheap Italian motor, about 2 kilowatt, and it basically drives flywheels like in your car, and you store the energy in the flywheels, the energy I want for the earthquake. And that bit is very straightforward because I can run the electric motor slowly and build up the energy in the flywheels. The trick really is, and this is what took 6 months of my life, is to develop this fast-acting clutch, bit like in your car again. So the clutch needs to engage the reciprocating rod in less than about 15 milliseconds. And it is not easy, I can tell you that. And once the clutch is engaged, basically it will transfer the reciprocating motion of the rod into the shaking of the box. Because it's so simple, it can work up to G levels of 100 G, no trouble. You can choose the frequency. I'm giving it in prototype scale, anywhere from 1 to 5 hertz. You can choose the size of the earthquake up to 0.4 G, and you can choose the duration of the earthquake. The frequency we can change because I can decide what angular velocity I'm going to run the motor at. So I have an inverter and run the motor to the speed I want. I can have the duration, I can decide how long I want to hold the clutch for on a timer. And magnitude is I can change the offset distance and get earthquakes of different size. This took me about a couple of years to build, but it produced more than 12 PhD students. So it's done very well. And there's nothing wrong with it. We recently decommissioned it because the other actuator has been taken over, but it is really simple and easy to use. And it will produce earthquake motions like this. So finally, here. So this is very clean sine wave motion. It's a mechanical actuator. And if you do the fast Fourier transform of that, you can see it's produced at about 0.8 hertz prototype scale. It got concentrated energy. So sine waves have that nice feature that you can have all the energy at one frequency. And then once you apply this, you can see how your soil model, structure model is changing. What is the frequency response for that? So all it is, as I said, set of flywheels. We oscillate the reciprocating. You run this motor. It's like the old choo-choo train, steam engine, right? So you convert rotary motion into reciprocating motion, and the clutch basically engages the rod. It's very straightforward. And once this is twisted, this twist here makes the table shake back and forth. And because I can adjust the pivoting distance between here and here by using a three-phase motor, I can get earthquakes of different amplitudes as well. That is the cheap and cheerful earthquake actuator. The more expensive version is this one. This is the servo hydraulic shaker. Again, we built it. We bought some critical components, but it's all done in Cambridge engineering department. This can go up to 80 load of about 200 kilograms. And the big party trick this one has is it can do realistic input motions. It can also do sinusoidal motions, but we can also do realistic input motions. And we designed this so that it can receive all the special model containers we designed for SAM actuator can also go on this, so that we are not rebuilding everything. So we built it, and first time, that is the soil model on the ESP box. I'll come to ESP box later. And this is what it can do. It can apply example of Kobe motion, Port Island recording, or it can do Imperial Valley, very high frequencies, and spread out all across. So this is the time trace. This is the fast Fourier transform. So you can see almost at every frequency component, there is some energy. Okay? I'm not saying these are good, but if you want, you can apply. These days, what we do is, we do all our research with sinusoidal motions, but either before or end of our sequence of testing, we'll do one or two of this Kobe motion and Imperial Valley, so that if there are any frequency dependent ones, we also not going to miss it. But we are not going to use this as the main thing. Just for completeness sake, there are electromagnetic shakers. This is in Chiyo University. There's one in Shimizu Corporation in Tokyo as well. And these are basically electromagnetic shakers. I built one for our drum centrifuge, which kind of works, but we never used it in anger. Only fourth year students did their projects on it. Electromagnets are quite nice and easy, but the problem is that to get enough oomph or force to shake it, you need quite a big DC current. And the DC current needs to be of the order of 1000 to 1500 amps. So you need to send that much current through the slip rings onto the centrifuge. And that is really where the Japanese, even they found they couldn't shake big models on that electromagnetic shaker. Otherwise, it is works very easy, and you can buy an electromagnet probably in Jalandhar market. It's they are everywhere, right? Electromagnets are so common, so it's not hard to get it. But on a centrifuge, we need to get the current, basically power, voltage, and current onto them. Okay, the bit I didn't cover so far is the the semi-infinite extent of the soil. This is typically, again, embarrassingly, all these slides are coming from my PhD thesis long time ago. But basically, what you have is if you got a tower, piles, and raft, this is what we are looking at. So we want to do this kind of shaking, but in reality, you have semi-infinite extent. So horizontally, you have no bound. So you expect the soil to run, at least relative to the dimension of the building, you consider that to be plus infinity to minus infinity, right? You must have come across this before. Now, how am I going to create that in a centrifuge model, which is only this long? It's about 700 millimeters long. So at 100 G, it's like 70 meters. But it is a clear boundary, right? So if I make this just like a rigid boundary, when I shake it, the soil inside is going to get slapped by the end walls. It's like, as it moves, you are slapping the soil silly. So we shouldn't do that. So we came up with this idea of having so that is an aluminum ring, rubber, aluminum ring, rubber, aluminum ring, rubber, and so on. And we can adjust the thickness of these rubbers. So what we do in this equivalent shear beam concept model container is I can work out for a given height of soil what the shear deformation in the soil is going to be for a given earthquake. So typically in the first mode, it probably will do something like that, this solid line, right?
You have to simple shear.
Yes, but this is dynamic, right? It's doing both sides. So in the other half cycle, it goes the other side. Simple shear is only one side. Yeah, a similar idea. So what we are trying to do is to match this curve stepwise. So the aluminum section doesn't deform, but the rubber deforms a lot. So we make the bottom rubber ring quite thick. And as you come to the top, the thickness of the rubber rings gets smaller. So stepwise, we can match the shear deformation, which means that when I'm shaking, the container is also deforming like this, and the soil is also deforming the same way. This is how we can avoid the P wave generation at the ends. That's one idea. This is a tiny model container. So once we made that, we discovered that as the problems go bigger, we need bigger containers. One of the reasons we had to build this is there was some guy, my former colleague and compatriot, called Scott Steedman, and he said that, soils beyond a certain depth can't liquefy. So he said, mostly in the field, we have evidence of liquefying the soil only the top 15, 20 meters max. And he said, below that you can't liquefy. And I said, that's rubbish. Yeah. So, but I had to prove, right? So we built this one. This models something like 40 meters of soil depth. So if you take the whole of this soil at prototype dimensions, this is 4 times bigger than what E-defense machine can test. So shake tables are therefore cannot handle this kind of large soil volumes. So we showed that liquefaction can, in fact, if you shake it strong enough, it can go all the way to 40 meters. There's no such limit as a depth limited liquefaction. Yes. Yeah. And if stupid people go and say stupid things, codes tend to be the first ones to copy them. So I don't believe in codes. Okay. The other concept we have is this laminar box. This laminar box is effectively like having zero stiffness. So you have each of these as aluminum lamina and they got bearings in between. So when you shake it, the box has no stiffness. So it will basically go wherever the soil wants to go. And I'll show you some examples of use of this laminar box in the afternoon, in the lecture after tea. So it actually, especially for lateral spreading problems, you cannot do those in the ESB box. We had to build this. So a lot of our research is kind of driven by the need. You want to model a problem, what are the limits? Then you go and try and do improve your this thing. So this is also works very, very well. We tried so outside Delhi and elsewhere. A real properly designed landfill should have a clay layer, a geomembrane, base layer, a geomembrane, and it goes onto the other side as well, right? And after the waste is filled, you also have to put a top cover. Now these type of landfills have been built in California, Southern California, since about 1950s. 1950s, okay? And nobody has worried about if I have sand below and if I get an earthquake, I could liquefy the soil and that can lead to uneven settlements. And these things are very sensitive to cracks. It's a clay liner, right? Clay is not great at carrying tension. So it is very easy for it to crack. Then I'm only relying on this geomembrane to hold my leachate or the horrible stuff that forms at the base of the landfill. So first thing was that I had a colleague and friend in Santa Clara University called Suki Singh, and we said, he was working with MSW, and I said, did you think of this? And I said, no, I haven't thought about it. Let's do environmental agency. So this is a new class of problem. Nobody has attempted this, and you can try it, right? We can do centrifuge test. So we create the model and subject it to earthquake shaking, and only the foundation soil can liquefy. This one should not liquefy. The clay liner will not liquefy. It's only driven by displacements. So we created a model. This guy is very good, Tushyantan. And so our centrifuge model was like this. So this is the loose sand which can liquefy. We fill this with model waste and the clay liner. So we had to create model waste, unlike IIT Delhi, where there was a guy who actually went to real landfills and got the waste to characterize it. My students, if I send them to real landfill, they will not come back to the lab. They will leave the program and go somewhere. So we said, no, we'll create a model waste which has the same compressibility and other characteristics as real waste. So we made model waste on this and created the model. This is good 25 years ago. We had like a webcam which is looking here because we're expecting to see liquefaction at the back. So that's the cross section, that's the real model. Very easy to understand. We also had other tests where we were looking at the tension in the geomembrane. So we could see how much is the displacement of this and what is the tension in the geomembrane using some arrangement. And that is the view of the camera looking at the back of the landfill. So we could see the liner movement. So post-earthquake, we could see big cracks develop at the back and the whole thing tilted. The landfill liner fell back and started. So the waste itself we filled with some green fluid so that if it leaks out into the foundation soil, we can see it. So post-test, this is in-flight picture, obviously. We could see the soil here is now gotten wet because of the pore pressure generated below. The water came up and created these kind of sand boils behind, because we held the water table about here, and so the water coming to the surface means there has been liquefaction. We also had instruments to tell us how much pore pressure we're getting and also how much is the liner movement. Here the liner was moving, say something like 1.5 to 2 millimeters. 2 millimeters times I think this test was done at 50 G. So it will be about 50 to 70 millimeters of movement, and that's big enough to crack the clay. So you can study real problems like this, and even when things were not previously studied, and when people didn't know there was a problem. So we thought, wow, we got this data. All this work is published in geotextiles and geomembranes and other journals, ASTM for model waste and so on. So we had good set of publications. Then we went to Environmental Protection Agency in Washington and said, we had a meeting with them, Suki and me on one side and all these guys on the other side, and said, look guys, you got a problem. All these old landfills may have been subjected to many earthquakes in the past and they would be leaking. So you really need to go and check for groundwater quality around the old landfills. And then they said, no. Our job as Environmental Protection Agency is, if the landfill owner comes and says, we feel our landfill has leaked, then we will go and investigate. Otherwise, we won't go. And I said, this is stupid. I was also much younger then, and I was very hot under my collar, and said, your job as the Environmental Protection Agency in the US is to protect the citizens. That is your primary job. Why will any landfill operator will come to you and say, oh, maybe the last earthquake created problem for us and all this thing has leaked? They'll never say that, because that's going to cost them money, right? It is so stupid to say, oh, the owner of the landfill should come and ask us. Anyhow, that didn't go down too well. We got no funding from them, but the research is still there. And I'm sure something similar will come up in Delhi and other places when we start to build proper landfills. So at the moment, we are not without proper landfills. Once you start building proper landfills, you also have these kind of earthquake-related problems. So we're kind of 2 steps away. So I'm not suggesting any of you will start research in this straight away, but maybe your children should look at that, because we will come there at that time. Okay, I'm going to stop there, and then we'll go back to pile foundations this afternoon. Any questions? Yeah.
Does this surcharge increase the density of surcharge we have here in
Where?
landfill glass lines?
Oh, okay. Yeah. Basically, yeah. A normal landfill will have, so this is typically about 25 meters. Yeah. And on the top, you pile up another 25 meters or 30 meters. Yeah. So this is the real problem. We are not modeling all of that. So we are only modeling this bit, right? So what we did was that, okay, we filled the waste till here, but I can't make the model come out of the centrifuge container. So we put surcharge on the top to simulate that stress. Okay, using lead shot.
So this surcharge can be applied pre of the before earthquake.
Yeah, it's there before the start of the centrifuge. So you get some settlement under the application of surcharge.
So settlements of that.
Yeah, those are all monitored, so we know how much it would settle back. So you can rework the density of the waste. Normally, we don't make silly mistakes like that. Normally, occasionally you may catch me, but the student is very good, so he wouldn't make stuff like that. Okay, any other question? What do you guys think of this whole simulating earthquakes in the centrifuge? When it starts to work in Bombay, I suggest you all go and have a look. It is very exciting when it happens. It's so quick, and the damage you see in the model is quite visual. So it's good fun. Okay, if there are no more questions, we'll stop there, Professor.